course Advanced Reaction Engineering. So, in this course we are discussing solid catalytic reactions. So, the reactions and diffusion. So, that part already have started. So, it is the continuations of that part. So, here in the last class we have discussed the reactions and diffusions. In that case internal effectiveness factors that we will discuss today's class. So, means internal diffusion factors we have discussed about the in our last class we have discussed or derived the second order differential equations for a spherical particles. So, when there is a reactions and diffusions is there, and based on that using two boundary conditions we have solved that second order differential equations. Then the concentrations profiles that we have discussed means when there is a reactions and diffusions is there, how the concentration changes means reactant molecules when it is diffusing from outside of the catalyst surface to the inside of the catalyst pore. So, at different locations of the pores the concentration changes. So, what would be the concentrations along the length of the directions of the pores means along the length of the pores. So, by changing radius of that spherical particles or catalyst. So, then we can say the concentrations that way it would vary from high concentration at the surface and then with inside of the pores gradually it is decreased. So, that we can get an idea about the changes of the concentration, and based on that we can say whether the reactions is controlling surface reactions or diffusions. Okay. So, now also that we have evaluated or expressed the Thiele modulus also, that is phi. So, in terms of other parameters we have expressed. So, now internal effectiveness factors we express in terms of Thiele modulus, internal effectiveness factors in terms of Thiele modulus. So, Thiele modulus expressed in terms of phi and internal effectiveness factors expressed in terms of eta. Okay. So, what is the effectiveness factors or internal effectiveness factors? So, it is basically two rate. So, means when a spherical particles you have taken. So, we know this is the surface concentrations and this is the pores. So, here the concentration is Ca and the surface concentration is Ca S surface concentration. So, if the concentrations surface and inside of the pores of the reactant molecules are different, then of course, the inside rate of reactions and outside surface of the means surface rates that would be different at this particular locations. Here let us say we are expressing minus RAS rate of the reactions at surface reactions concentration. Let us say we usually express rate equals to this minus RA equals to K into Cas. If Ca is there, then rate would be this. If inside rate is concentration is this, then minus Ra would be K into Ca. So, these rates and this rate both are different since concentrations are different at different locations inside of the pores and outside of the pores or external surface or outside of the surface. Concentration reactant concentration are different due to the diffusions or the concentration would be different, therefore, rate would be different. So, in real case whenever we design a catalyst, so I said we can design a catalyst this way, very small particles, particle dimension or catalyst dimensions we can change accordingly this. So, depending upon that any dimensions we can consider for our catalyst particles. So, whenever we design and whenever conduct any reactions in any packed bed reactors or gas solid reactions, then we are expecting that the rate would be uniform or homogeneous everywhere inside of the catalyst, outside of the catalyst. So, then we are get a linear rate means throughout the rate. So, then we can get actual or high rate of the reactions, high rate of product formations, but in real case we have to give the catalyst a particular shapes and particular dimension or diameter. So, whence dimension is there, so pores formations would be there inside of the catalyst, pore distribution should be different, then rate would be different. So, then the effectiveness factors and its value whatever that would come. So, based on that we can say that the whether the catalyst is means the rate we are expecting that is coming or not, or whether there is diffusions or not. So, this actually effectiveness factor actual rate of the reactions to the rate of reactions that would results if the entire interior surface were exposed to the external pallet surface conditions CAS TAS. Okay. So, it indicate actually here concentration is different, here concentration is different. So, actual rate of reactions, and if inside of that catalyst components exposed. So, then this Ca equals to CAS, then there is no concentration gradient, means surface concentration or pore mouth concentration, and inside of that pore concentration are same, there is no concentration difference. If there is no concentration difference, so there is no diffusion does exist inside in the catalyst surface or during reactions. So, therefore, then everywhere we can get the same or homogeneous rate. Okay. So, then it is means not possible always. So, means some gradients or concentration gradients or difference would be there. So, therefore, the rate or effectiveness factor is coming with the Thiele modulus. So, eta is expressed minus R A by minus R A S minus R A primes minus R A prime A S, or we can write this way. Okay. So, this is actually ratio of two different rate. Okay. So, now this rate usually this effectiveness factors we usually express in terms of the ratio of two different rates, and the rates usually expressed in terms of per unit volume. Okay. So, rates, what is rate equals to per unit volume per unit times, usually rate express moles per unit volume into per unit times. So, usually this way we can express the rate of a reactions. Okay. Moles of A, that is decomposed per unit volume per unit times. Okay. So, if we multiply with that with the volume, so then rate would be moles per unit times. So, this way we express the rates. So, these rates minus R A, if we are multiplied with the catalyst volume, bottom and top and denominator both the sides we are multiplying with the catalyst volume. So, then these rates we are expressing in terms of this rates changes of the moles Ma by MAS, Ma equals to mole per unit times, MAS also mole per unit times. Okay. So, MAS indicates in the surface conditions, are A, that is inside of the pores the rate. Okay. So, basically volumes part we are eliminating. So, okay. So, now this MAS we can write equals to minus RS into 4 by 3 pi RQ, that is the volume of the catalyst. If R is the diameter of the catalyst or radius of the catalyst, so then we can get the volume of that particle equals to. Okay. So, that we are multiplying here. Okay. So, then we can write this, and R A minus R A is equals to K into C A S. So, this way the mass we can rate of mass transfer we can find out M A S equals to this. Okay. And so M A we have find out in our previous lectures. I think M A we have defined M A equals to also this way, flux into multiplied with area, that way we have defined, and flux equals to this. So, we have dimensionless forms this way Ma we have expressed rate of changes of the moles per unit times we have expressed multiplied flux with the cross section area or surface area. So, then this Ma at lambda equals to 1 equals to this. Okay. So, we have this, and this psi equals to Ca by Cas equals to this. We have developed this equation this is the concentration profiles for spherical particles first order reactions we have expressed in dimensionless forms. This also equations we have derived in our last class, and this also we have discussed in our last class. So, Ma equals to this in the dimensionless forms, and Thiele mod psi, that is the dimensionless concentration, is this we have expressed in our last class. So, now here these dimensionless concentrations profiles or equations that we have discussed or derived, that we are differentiating with respect to the lambda and putting lambda equals to 1 once we differentiate this with respect to the lambda and putting lambda equals to 1, we can get this, and putting lambda equals to 1, so we can get this. Okay. So, thence we can get that d psi by d lambda equals to this, and then so we are substituting this here. Okay. So, we are substituting this rate per unit times changes of the moles per unit times. So, this is the rate, actual reactions rates is this, and MAS we have discussed this. So, now if we want to get effectiveness factors, then so we need MA and MAS. MAS is this and MA is this. So, now both we are substituting in that equations, then eta equals to MA by MAS. So, MA by MAS equals to, after simplifications we can get this. Okay. So, we can write that eta equals to 3 by phi 1 square phi 1 cot h hyperbolic minus 1. So, this is the relationships in between effectiveness factors and Thiele modulus. So, Thiele modulus we can express this way, phi 1 equals to r into square root of q 1 by d e. Okay. So, this is the Thiele modulus, or this we have discussed in your last class. So, eta equals to this. So, if we know value of phi Thiele modulus, so it has some value, let us say 0.4. So, we can substitute here what are the place. If you simplify, then eta value we can find out. Eta is the effectiveness factors. I said eta equals to rate by rate, two rates. See, this is rate at surface conditions, this is overall rate. So, then it has some value, let us say 0.9 or 0.8. So, by that way we can guess, means if once we know the effectiveness factors, eta let us say very close to 1. So, eta usually two rates, its value should be 1. So, if it is 0.9, then it is very good. If eta value equals to close to 0.1 or eta value may be 0.1, very low value or very high value. So, it indicates difference, or it signifies difference, means means performance of the catalyst or the catalyst you have designed. So, reactions and diffusions and concentration of the reactant outside and inside of the pore, how they are at different locations, that means the catalyst you have designed, how they are behaving. So, with the help of effectiveness factors we can guess. Okay. So, now Thiele modulus and effectiveness factors if we plot. So, here's these equations we have developed. So, here's means so, this is the equations. So, eta and effectiveness factors. So, here's phi value 0 0.0, 0 0.1, 0 0.4, 1, 2, 10, 20, like that, one by ones we will select and put in these equations, then corresponding eta value we will get. So, if we plot them for, let us say it is a first order reactions, from the beginnings we have considered. So, if it is first order reactions, then Thiele modulus for first order reactions would be this, and then the nature of the effectiveness factors and Thiele modulus would be like this. Okay. These curves we will get for first order reactions. So, eta and effectiveness factors. So, here maximum effectiveness factors would be 1. So, 1. So, this value. Okay. Similarly, means at the beginnings we have considered it is a first order reaction, therefore, the nature of the curves would be like this, and catalyst was spherical. If we consider from the beginning 0 order reactions, then Thiele modulus would be this. If it is second order reactions, so then it would be like this. Okay. So, and natures, corresponding natures of these curves would be like this, means similar trends, but different. It would be for 0 second order spherical particle, it would be 0 order spherical particle. So, here I said small value of Thiele modulus and large value of the Thiele modulus. If small value, then effectiveness factor is this, and if small value, a large value of the Thiele modulus, then effectiveness factor should be this. So, this way we can say that means Thiele modulus easily we can predict, means the purpose of express the reactions in terms of Thiele modulus or effectiveness factor is that quick estimate. So, means what a particle or catalyst we have designed. So, let us say this here is R value, means this size of the catalyst we have designed for a n equals to first order reactions, R value is known. So, then we can say we can put all those components Thiele modulus or effectiveness factor easily we can find out, and then we can predict that what would be the means either it is diffusion control or reactions controls. So, then suddenly we can change catalyst particle difference for the same reactions. So, then here also we can predict eta and phi value, and based on that we can say the whether diffusion would be the control or reactions would be controls. So, here you can see here when Thiele modulus is very small value, effectiveness factor is close to 1. So, then we can say reactions rate is limited, and so when Thiele modulus is large value, then effectiveness factor should be like this, and then so we can say that internal diffusions limited the rate of the reaction. So, Thiele modulus depending upon the Thiele modulus, it is a small or Thiele modulus value is large value. So, if it is small, then reactions limited or reactions rate of the reactions is control the reactions. If Thiele modulus is value is large, then diffusions means internal diffusions that limit the rate of the reactions. Okay. So, depending upon the Thiele modulus means value of the Thiele modulus, we can say that whether reactions is rate is limited by reactions or diffusion. So, always whatever means for let us say packed bed reactor, solid catalyst we are going to design or designing with the reactors, we have to design the catalyst also, we have to set the reaction first, and so order of the reactions, rate constant, everything is known. Once we design the catalyst particles a particular diameter or dimensions, then which dimensions we have to select, means either very small particles we will consider or very large particles or intermediate particle size we will consider. So, depending upon that we can eliminate the diffusion part. So, always our objective should be whenever we are going to design a catalyst, so that diffusion we can eliminate and reactions should be controlled or limiting for that particular reaction. So, then easily we can means that should be, then we can get higher conversions, higher yield, higher selectivity, that would be objectives. Okay. So, now these are the means when volume changes is there. So, effectiveness factor and volume changes how they are related by changing Thiele modulus, that is given. So, that is for first order reactions and spherical particles when volume changes is there. So, how there it is look like this when Thiele modulus is very low, then it would be like 1, there is no changes, means volume changes does not affect, and so when Thiele modulus is let us say 6, it would be like this. Okay. So, some changes are there, means with the volume changes of the reactions. So, now whatever I said, so this is the relationship that we have discussed. So, internal effectiveness factors for first order reactions and spherical particles. So, this is the correlations or relations that we have developed. So, let us say particle diameter become very large, phi n decreases, so that the effectiveness factor approaches to 1 and the reactions or surface reactions limited the reactions. Okay. And when this is the case 1, this is the case 2, or observation 2 you can say. So, when Thiele modulus is very large value, it actually indicate here or here large value 10, 30 whatever, the effectiveness factor is very small. So, that already have discussed. So, and reactions diffusion reactions is limited. Okay. So, when Thiele modulus is very large, okay. So, these equations we have discussed, means and when Thiele modulus is large we can approximate that, and when Thiele modulus is small is like this. So, here when Thiele modulus phi is very large, so then phi 1 minus 1 we can consider phi 1. Okay. So, thence the equations, these equations will be converted into this eta equals to 3 by phi 1. Okay. For large value of Thiele modulus, eta equals to 3 by phi 1 for first order reactions, when means this component we can consider this. Okay. So, now this is for when Thiele modulus is very large, and we know Thiele modulus and equals to this, we can substitute this here. So, then eta equals to 3 by r square root of dE by k 1. So, effectiveness factors here means particle size, reaction rate constant, effective diffusivity, how they are related with effectiveness factors. So, now effectiveness factors here means these are the components are related to each other. So, if we vary one components, other components would give a particular value. Okay. Now, overall rate of reactions in terms of Thiele modulus, the overall rate of the reactions in terms of Thiele modulus, that already have discussed. So, here effectiveness factors we can express minus R A by minus R S. So, here minus R A equals to actual rate of the reactions equals to effectiveness factor minus R A S. So, eta into K 1 C S. Now, eta we can substitute here for large value of the Thiele modulus. So, here our overall rate of the reactions we can write this. So, minus R A 3 by R square root of K 1 S A rho C D E into C S. C S is outside, I think. So, this is the means from definition of effectiveness factors. By putting effectiveness factors, we can write the rate equals to this way. Okay. So, rate we are writing this way. So, here whenever we are conducting a reactions inside of the spherical particles, these spherical particles, catalyst particles, spherical catalyst particles, and we are conducting A is going to B. Here reactions rate constant small 1 K 1 we know, surface area of the catalyst we know, and effective diffusivity of this catalyst particle know, surface concentrations if we know. Okay. Density of the catalyst particles is known. Okay. So, now this rate means these are the components if known, then R A how affect on these parameters. Then when decreasing the radius means catalyst particles, this is the R's, if we decrease the catalyst means large particles to small particles if we make. So, then if rate of the reactions will decrease as the radius or the particles make smaller. If we make smaller particles, larger particle to smaller particles, so rate would decrease. Okay. And increases the temperature. So, to increase means if want to increase the overall rate of the reactions, so then means if we want to increase these rates, then R we have to decrease and surface concentration we have to increase, specific surface area have to increase. So, increase the temperature, reactions rate constant K as a function of temperature we have discussed at the beginning. So, if we want to get or increase the rate of the reactions, then we have to decrease the catalyst particles, we have to increase the reaction temperatures, we have to increase the concentrations, C S directly proportional minus R A directly proportional to the C S, surface concentration have to increase to get increase the rate, and inversely proportional with R, and increase the internal surface area also. If we increase the surface area of the catalyst, then the overall rate of the reactions we can increase. Okay. So, this is the take home message, and also the Thiele modulus we can express in different way also for nth order reactions or generalized that. So, this is phi n's we have discussed, phi n square equals to this, and for nth order reactions. So, or effectiveness factors if you substitute that. So, this way also we can express for nth reactions. Okay. Thank you. So, today is up to this. Thank you.